Now that we have information about inverse trigonometric functions, let's work some problems. This problem says the inverse cosine of 1 over the square root of 2. And let's understand that this is a request for the angle whose cosine is 1 over the square root of 2. And let's see, is this a cosine value? Yes, it's vaguely familiar. Let's just say we're not using the calculator here, otherwise we could just punch this in and make the calculation. So we want to do it by hand, and if this is one of those familiar right triangle situations that we've had in the past and we can't recall it, then what we do is we slide over to the side and we sketch a couple of right triangles. Now, one of the right triangles you want to sketch right quick is the one with a 60-degree angle and a 30-degree angle. And remember, in this right triangle, the short side is opposite the small angle, so this is the 1, 2, square root of 3 situation. The other triangle you want to sketch is the one with 45-degree angles for the acute angles. And we only need information about one of them because they're kind of like the same. But at any rate, it's the 1, 1 square root of 2 situation. Now, from the perspective of what angle is it the case that the cosine of the angle is 1 over the square root of 2? That's really what is the request here. Oh, it's this one, because cosine is 1 over the square root of 2. Oh, it's 45 degrees. So we come back over here, 45 degrees, and that's our answer. Now, if we want to, we can convert this into radian measure, or we could have thought of these triangles as being measured in radians as well. Arctangent, the square root of 3, means that we're looking for the angle whose tangent is the square root of 3. So we look over here, oh, the square root of 3, there it is. And let's see, tangent is opposite over adjacent, so square root of 3 over 1. Oh, the perspective is from this angle, so the angle is 60 degrees. And once again, we could convert to radians very easily. Arcsine, square root of 3 over 2. Ah, the one that involves square root of 3 is this one. Now, from the perspective of which angle do we have the sine as the square root of 3 over 2? Now, that's opposite over hypotenuse, square root of 3 over 2. Oh, the perspective is, again, from this 60-degree angle. Let's use the calculator to find these. Arc cosine negative 0.647. Arc cosine. Now, that means we want the angle whose cosine is this negative value. Now, we know probably at the beginning that the cosine of angles is positive in the first and fourth quadrants, but negative in second and third. And we know that in the world of inverse functions that we're talking about angles that appear only in the first and second quadrant for the inverse cosine. All right, and therefore this is going to be a second quadrant angle. Okay, because it's negative. Okay, now, to use the calculator, we do this. We press second, and then cosine. The second function on all of the trig functions are the inverses of them. So this is the inverse of the cosine. Okay, so it's like arc cosine or inverse cosine of, and then you just enter the number and press enter. And depending on the mode of your calculator, it will give you the answer in degrees or in radians. If you're in degree mode, the angle is approximately 130.3 degrees. I have it written off camera here. I'm reading it and writing it. I can't calculate these things on my own, you know. And if you're in radian mode, the calculator says that it's 2.27. First of all, for cosine x, we know that the graph looks like this, and it continues in this pattern forevermore. And so the function, the graph of the function fails a horizontal line test rather miserably, and so therefore the inverse will not be a function. We have to limit the domain in order for the inverse to be a function. Now we have a really nice, almost built-in limitation on the domain here. Remember, we want a domain or an interval over which the function takes on every value within its range, that is, every value from -1 to 1. And that occurs within the interval from 0 to pi. So that then will be the interval over which we define our function and therefore will allow us to generate an inverse that will be a function. All right, so let's write that up here. We're limiting the domain to 0 to pi. So domain, zero is less than or equal to x is less than or equal to pi. Range, we know the range values go from -1 to 1, so it's -1 is less than or equal to y is less than or equal to 1. That's only important for us to identify aspects of the inverse, and we know to generate the inverse, we're going to go through a process similar to the one that we did with the sine function, and it is that we'll have, well, I can designate, remember the designation for inverse function, it was this. I didn't use it over there for sine, but I certainly could use it, that f inverse of x is equal to inverse cosine of x. You see, it's like that, and a very customary and workable way to write it is simply that y equals inverse cosine of x. All right, here's the important thing, though, in terms of calculation and all of that kind of thing, that the domain of this inverse function corresponds with the range up here, and as expected, it's -1 is less than or equal to x is less than or equal to 1. That just means that we can only take the inverse cosine of numbers that are between -1 and 1. All right, now the range. Range corresponds to the domain of the original function, and that's 0 to pi. So our range is 0 to pi. 0 is less than or equal to the y values that come out of this, and those y values are less than or equal to pi. And what that really implies is that when we take the inverse cosine, that is, we find the angle whose cosine is x, then that angle is going to fall in the first two quadrants. And to emphasize it further, using angular measure, this is 0 is less than or equal to y is less than or equal to 180 degrees. So we're confining ourselves to the first two quadrants, you see, of our coordinate plane, or of our unit circle, if we'd like to think about it like that. Here's a situation in which we'd like to solve for the length of a side and the size of the angle. Now, here we weren't solving, in this previous problem, we weren't solving for the angle size, but we can solve for the angle size. Now, consider that, first of all,